Hey everyone, in this video I'll explain different electromagnetism equations involving forces and try to help you understand the relationship between these equations and the different circumstances in which you'll use them. Here are the four electromagnetism formulas or equations I'll discuss in this video. We'll begin by discussing the force that acts on charges when they move in magnetic fields. Specifically, when we talk about charges, we refer to any particles with positive or negative charges, such as protons, which are positively charged, and electrons, which are negatively charged. Whenever these charged particles move with a certain velocity inside a magnetic field, they are acted upon by a force. And the equation associated to determine the nature and the magnitude of this force is equal to 𝑞𝑣𝐵 sine theta, where Q is the charge of the particle in coulombs, V is the velocity of the particle in meters per second, and B is the magnetic field strength in teslas. The angle theta in this equation refers to the angle between the velocity of the particle, which is the direction in which it's heading, and the direction of the magnetic field, keeping in mind that both V and B are vector quantities. Since this equation contains the variable charge, velocity, and B, this will help you remember that you will need to use this equation to determine the force acting on a charged particle, Q, whenever it's moving inside a magnetic field, both V and B. The angle theta in this case is between the only two vector quantities used to determine the force. The vector quantities, as I mentioned earlier, are velocity V and the magnetic field strength B. So the angle theta is between the velocity of the charge and the direction of the magnetic field. In this diagram, the electron has a velocity going towards the right of the screen, while the magnetic field strength is heading into the page. So the angle theta between the velocity and the magnetic field strength is 90 degrees, or perpendicular. Now let's talk about current carrying conductors. Remember, in electromagnetism, an electric current is defined as moving charges in a conductor. Specifically, current is calculated by dividing the charge in coulombs over the time, t, in seconds. Since current is moving charges, whenever there is a current in a conductor, essentially there will be moving charges, primarily electrons, in this conductor. And when a conductor is placed within the magnetic field, these moving charges will also be moving within that magnetic field. As we previously explained, whenever there are charges, whether they're positive or negative, and they are moving inside a magnetic field, there will be a force produced acting on the moving charges. Now in this case, because the charges are moving within the conductor, the force will be acting on the conductor itself. So we can start by looking at our original equation, F equals to 𝑞𝑣𝐵sin𝜃, which is the force acting on charges moving in a magnetic field. Now in this instance, because the moving charges is in the form of an electric current, we can use our previous equation, I equals Q over T, to redefine Q as the product of I times by T. And the velocity of the moving charges will be constant, given that the magnitude of current is constant in the conductor. So V here is also equal to the length of the conductor, which is the distance over which the charges will be traveling, divided by the time the charges will take. The time in this case and the time in the current equation are the same time. So in this equation, we can cancel them out. This will transform the original equation into a new equation that we can use to determine the force acting on a current carrying conductor inside a magnetic field, 𝑙𝐼𝐵sin𝜃. In this case, I is current in amps, L is the length of the conductor that is inside the magnetic field, this is in meters, and B is of course the magnetic field strength, again in teslas. Now the angle is between the direction of the moving charges, that is the current, and the direction of the magnetic field, B. You will use this equation to determine the force acting on any current carrying conductor when they are placed inside a magnetic field. And the angle theta in this equation is between the direction of the current and the direction of the magnetic field. Now let's talk about the force between two parallel current carrying conductors. By way of review, in electromagnetism, A current carrying conductor will produce its own magnetic field, which is a radial one surrounding the straight conductor. The magnitude of this magnetic field can be easily calculated by the following equation. Mu naught times by I over 2 pi r, where mu naught is the magnetic permeability constant defined by the following value. I is the current traveling through the conductor, and r is the distance at which you're measuring the strength of the field from the conductor in meters. So of course, as you move further away from this current carrying conductor, the distance r increases, which will result in a smaller value for the magnetic field strength, so it gets weaker. Now, in a setting of two parallel current carrying conductors, what you need to understand is that the force between these current carrying conductors is essentially the same force as the one that would act on a current carrying conductor if it's placed inside the magnetic field. Suppose if we just focus on the first conductor on the left-hand side, this conductor carries a current, and when it's placed next to another parallel current carrying conductor, it is inside the magnetic field of this conductor, which goes around like this, as we just previously discussed. In the presence of this conductor, it will experience the force given by the equation of I/L/B sine theta. The magnetic field strength is, of course, the field strength, the magnetic field produced by the other current carrying conductor on the right-hand side. And this can be determined by using the equation that we discussed earlier. So we can replace the value B by this entire expression, which gives us a slightly more complicated equation. Now in this case, I1 refers to the current in the first conductor, and I2 refers to the current in the second conductor because it is the second conductor that produces the magnetic field that will result in the force. Sine theta, the angle theta here, refers to the angle between the current direction in conductor 1 and the direction of the magnetic field. Because the magnetic field around conductor 2 is always radial, the angle between the current and the magnetic field direction should always be perpendicular, which means theta should be 90 degrees, and the angle of sine 90 will be 1. So this simplifies the equation into F over L equals to mu naught over 2 pi times by the product of the two currents in the two conductors divided by R, which is the distance between the two parallel conductors. This equation is only used if you want to determine the force between two parallel current conductors. And the way you remember them is to realize that there are two values for current, I1 and I2, which are the values of current that flows through the two parallel current conductors. Now let's talk about torque. Torque is the net effect of a force applied in a rotational sense, and we talk about torque in the setting of a motor. The torque in the motor is due to the force that's acting on the current carrying armature, as shown by this simple diagram of a DC motor. The battery will supply the voltage which will cause the current to flow through the coils of the armature, and when the armature is placed within an external magnetic field, there will be forces acting on the coils. So in this example, the current will flow this way on the left-hand side and towards us on the right-hand side. If we use a right-hand palm rule, this will result in a force that acts downward on the left side of the coil and upwards on the right side of the coil. And this will produce a rotational motion and torque that goes in an anti-clockwise direction. We can calculate the torque by considering the simple equation for torque, which is Rf sine theta. R is, of course, the distance between the point at which the force is applied and the point at which the armature rotates, which is in the middle of the armature where the axle lies. So this is R over here. The magnitude of force that is applied on the armature is due to the fact that we have a current carrying conductor, that is the coil, inside a magnetic field. So we can bring back our previous equation, F equals to ILB sine theta. Now in this case, I'm using a different symbol for the angle, but we use phi here because I don't want to confuse the two angles together by using the same symbol. The angle theta in the torque equation refers to the angle between the force vector and the lever arm R. The angle in the second equation here refers to the angle between the current and the direction of the magnetic field. So these two are different angles. Keep that in mind. So when I substitute F with this entire expression, I will get this slightly more complicated expression for the torque acting on the motor. Now we have to keep in mind that the original torque equation we just derived is only due to one single force. We have two forces, one force acting downward on the left-hand side and one force acting upwards on the right-hand side. These two forces will be equal in magnitude at a given time, and they will produce the same direction of rotation and therefore torque. So the actual equation for torque is actually 2 times the value that we just derived. Now, sine phi here, where phi is the angle between the current and the direction of the magnetic field, this actually always remains perpendicular at 90 degrees as the armature rotates through its entire revolution. I explain why this is the case in its own video on DC motor, so make sure you check that out. So when the angle here is always 90, sine of 90 degrees will give us a value of 1. So this entire expression here can be removed because it only equals to 1. Now, if we examine the dimension of the armature closely, we realize that one side of the armature is L, the length of the current carrying coil inside the magnetic field, which is in my equation already. The other side of the coil, which is the width, is actually 2r, where r, remember, is the lever arm, the distance between the pivot where the axle lies and the point at which the force is applied. So the width here is double the length of r, so 2r. So 2 times by r, which is the width of the armature or the coil, times by L is really just the area of the entire armature that lies within the magnetic field. So this is area A. So I can substitute 2RL by simply A. This simplifies my torque equation to be IAB times by sine theta. And again, theta here, just to remind you, this is the angle from the torque equation. This is between the force vector and the lever arm R. Now, in most cases, when you have a motor that has multiple turns of coil in the armature, each turn of coil will produce its own individual force, which will contribute to the overall torque of the motor. So the more correct and accurate equation for torque is actually N IAB sine theta. N here is the number of turns. So let's go through that again. Torque equals to N, number of coil turns, times by A, current in amperes, times by A, area of the armature in meters squared, times by B, which is again the magnetic field strength, again in Teslas, and angle theta here is the angle between the lever arm R and the force vector that causes the torque in the first place. This concludes the video on electromagnetism equations. Hey everyone, if you found this video helpful, smash that like button and don't forget to subscribe. Want even more? Become a Patreon member for early access to videos, exclusive Discord discussions about questions on chemistry and physics, and live preparation sessions for your exams. Don't forget to head over to our website for topic tests and practice exams to further improve your understanding and learning.